Alright, now we're going to take a look at the acid-base properties of some salts. So there's some compound salts that ionize in water, and when you look at the salt itself, it doesn't particularly appear to be an acid or a base. It won't really have any H pluses or OH minuses, but because of the way it interacts with water, it hydrolyzes water and causes it to become an acid or base in solution. So keeping in mind something like ammonium nitrate, so we'll look at the example here. Ammonium nitrate, which is NH4NO3, so really that's NH4 and NO3 minus when it's in solution. So if you think of NH4 plus, that is the conjugate of a weak base. So it's the conjugate of NH3, it's the conjugate acid of NH3. And if we think back, the conjugate acid of a weak base is itself a stronger acid. So here we have a weak base, so this would be a strong conjugate acid. If we think of NO3, it would be a conjugate to, for example, HNO3. But that's a strong acid, and so this is going to be a weak conjugate base. So really that's not going to have any effect then on the acid-base properties of that guy. But let's focus on NH4 then instead. So if we look at NH4 when it's added to water, because NH4 is a strong acid, or stronger acid, when it reacts with water, what's going to happen then is water will gain one of the protons from NH4. And so then what we wind up with in the solution would be NH3 plus H3O plus. And then what we can see then from these products is we wind up with this H3O plus being formed in the solution, and the H3O plus causes it to have, a higher concentration of H pluses, which means that it will have a lower pH. So it'll end up having an acidic pH, so the pH will drop below 7 because that concentration of H plus increases. So just us adding this salt that's neither an acid or a base by itself, when we add it to water, it hydrolyzes the water, so it turns the water into, in this case, the hydronium, which increases the H plus concentration, which will lower the pH and cause this solution to be slightly acidic. And we would recognize this because NH4, that is the conjugate of a weak base, and so its salt then is going to make the solution slightly acidic. Whereas if we had a salt that was composed of the conjugate base of a weak acid, its salt would raise the pH as a result. Okay. Sometimes it doesn't need to be the conjugate either that is creating this pH adjustment in water. So if we take a look at iron chloride, so in this case we have iron which has a 3+ charge, so Fe3+. And what happens when iron chloride is in water? So the cation, so iron attracts the negative poles of H2O. So remember that H2O water, because of the electronegativity difference between oxygen and hydrogen, we're going to have a delta negative charge and a delta positive charge on these guys. And so what winds up happening then is this delta negative charge, this slight negative charge, is going to be attracted to this 3+, this very, very positive charge right here. And so the cations will be attracted to the negative poles of water, so the poles right there. That means that the iron 3+ right here is going to get itself surrounded by water molecules. When that happens then, the positively charged cation will decrease electron density in the OH bonds, and some of the hydrogens will end up breaking free. So let's take a look at this. I'll draw you a picture here in a second of what this is going to look like. But if we think of the iron in water, so when iron 3 is in water, it can also be written as FeH2O6, and that would be a 3+ charge on that. Okay, so these are called complex ions. We looked at these back in Unit 4 when we talked about the different reaction types. So this guy right here, what's happening is this is a ligand. It is a transition metal with a 3+ charge, and it's surrounded itself by these water molecules. So the rule of thumb is, in order to figure out, so there's 6 water molecules around it, whatever the charge on the molecule is, double it, and that's how many of the surrounding pieces would get around it. So there's 3 plus, we'd have 6 water molecules. 3 plus, and then those water molecules are neutral, so the overall charge of this molecule would be 3 plus. So when we put this cation, it's going to attract the negative poles, and we're going to get this complex ion right there. And this complex ion can set up equilibrium with itself, and it's going to turn into Fe, H2O, 2, OH, 2 plus. I'm sorry, H2O5. That should be a 5 right there. So what's happening then is this water molecule, we've got 6 of them in there. One of the water molecules in there is losing its hydrogen and turning into a hydroxide. And so that hydrogen would be drawn off to the side here. So this looks really complex, and it kind of is. That's why it's called a complex ion. So this complex ion, one of those water molecules, loses its hydrogen, and that hydrogen goes floating away as an H+. And that's why we write it as OH right there, and that's why the charge drops down to a 2 plus. So from a 3 plus to a 2 plus, because we lost one positive charge. Notice how the charges on both sides of this reaction balance then. So with the generation of this H+, that means that the concentration of H plus is going to go up, and therefore the pH will go down. So let's look at why this is. Alright, I know this looks crazy, but this right here, this is our iron molecule. So that iron, we can see, is surrounded by 6 water molecules, and the negative charges, those negative dipoles on all those oxygens, are going to be slightly attracted to the positive charge on the iron, and so they'll make kind of this little bubble around it where they surround it, and we have 6 of them there. As a result then, so all of the electrons are attracted to this +3 charge right here, and so that means the electron density is going to be pulled very, very closely into the iron. So all of those electrons are attracted to that positively charged iron. So as a result then, with the electrons getting pulled in, all of these little lines out here, those covalent bonds between the oxygen and the hydrogen, those all represent electrons. But those electrons are getting pulled towards the middle. While that pulling is going down, what's going to end up happening is some of these covalent bonds are just going to get too weak, and these little hydrogens will go floating away as H pluses. So with the electron density being pulled towards the center, the oxygens lose their grip on their own hydrogens, and the hydrogens float away. As a result of those protons floating into solution, the concentration will go up, and the pH goes down. Alright, so there's a couple things then that go into play as to how much the pH would be affected by this idea of the cations attracting the water molecules, causing them to release some of their protons. So the first thing would be the atomic radius. As the ionic radius decreases, so as the ions get smaller, it's going to have a greater ability to release those H pluses, thus driving down the pH. As the charge increases as well, so Fe3 plus would decrease the pH more than Fe2 plus, and by decrease the pH, that's increasing the H plus concentration. So that positive 3 charge means electrons are going to get pulled in even more, decreasing the strength of those covalent bonds even better than Fe2 plus would. Also, as a secondary result, as the charge gets more positive, the ion gets smaller, so the atomic ionic radius of Fe3 plus would also be smaller than it is for Fe2 plus. And the reason for this getting smaller goes in hand with the same idea. So ionic radius decreases, charge increases, and that's why Fe3 plus would lower the pH even more than Fe2 plus. Conjugate acids of strong bases will not affect pH ever. So something like calcium, strontium, barium, lithium, sodium, all of those have a large radii and small net charges, so therefore they're not going to affect the pH as much as something like iron 3 plus or other cations. Alright, anions. So anions that are conjugate bases of weak acids accept protons from water in order to produce hydroxides. So remember, if you've got a weak acid, it's going to have a stronger conjugate base. And by strong conjugate base, I don't mean it's a strong base, it's just stronger than the acid is. So it's going to produce that stronger conjugate base, which means that it will be able to accept protons from water to produce those hydroxides. Okay, so it hydrolyzes the water just like the cations did and causes it to become basic in this case. The conjugate bases of strong acids will not raise the pH, so things like Cl-, perchlorate, iodide, nitrate, bromine, and hydrogen sulfate, they don't accept protons from water because those are the conjugates of a strong acid, so they're not going to do this. It has to be the conjugate base of a weak acid in order to do this. So if we look at sodium acetate. So sodium acetate, you can see that that's probably derived from the same thing as acetic acid. It's going to be Na plus and C2H3O2 minus. And this guy right here, this acetate, that would be the conjugate of acetic acid. So it would be the conjugate base of acetic acid. And Na plus, that would be the conjugate base of sodium hydroxide, which is a strong base, so that's not going to have any effect on the pH. So when this is added to water, we would do kind of the same Bronsted-Lowry song and dance. So the water is going to donate a proton over to the acetate, and what that's going to make for us then is HC2, H3O2, and hydroxide, OH minus. So once again, we're producing, in this case, hydroxides, and hydroxides make things basic. So as the concentration of OH minus increases, the pH will also increase, and it'll become more basic. So the sodium acetate creates that acetate ion. That acetate ion is the conjugate of a weak acid, so it will hydrolyze water, turn water into OH minus, itself into hydrogen acetate, but that OH minus concentration will increase and pH will also increase. So anions that are conjugates of weak acids cause the solution to become basic. So cations make it acidic, anions make it basic. Okay, if we take a look here at a sulfate ion, so this is sodium sulfate, which ionizes in the water to produce sodium. That's going to be the conjugate of a strong base, so it doesn't really matter. And this here is sulfate, which would be the conjugate of HSO4 minus. So then the question is, all right, will that be strong enough to hydrolyze water? So let's take a look at the strength of HSO4. HSO4, 1.2 times 10 to the negative second. That is a fairly strong pH. I'm sorry, guys. I'm sorry, not a fairly strong pH, but it's a fairly strong ability to ionize. So that means HSO4 is still a fairly strong acid. So that means that since HSO4 is a strong acid, its conjugate base, which would be SO4 2 minus, is going to be weak. If it comes from a strong acid, it's going to be weak conjugate base. So this isn't considered, though, a strong acid by any stretch of the imagination. So SO4 2 minus will hydrolyze water, but very slightly. So there is varying levels that can happen here. Since this is still a pretty weak conjugate, that means it's not going to hydrolyze water very well, so the changes in pH would be negligible. So watch out for those weak acids and weak bases. Those are going to be the ones that have the most drastic effects on pH. Okay, another thing that can make a solution basic are metal oxides. So this one's already worked out for us. In this case, we're looking at magnesium oxide. That's our metal oxide. So magnesium oxide, when we put it in water, it's going to dissociate slightly into Mg plus and O2 minus. And it's that O2 minus that's going to hydrolyze the water and form it into OH minus. And so if we look here, O2 minus is formed and used up. And so as a result, the overall reaction is going to be MgO plus water is forming Mg2 plus and 2OH minus, which is actually a solid, so that will form a precipitate reaction. So if we dissolve magnesium oxide in water, it's going to precipitate out magnesium hydroxide. Now, magnesium hydroxide, if we think to our solubility rules, is labeled as insoluble, but now if you think back to last unit with KSP, all things that are insoluble are actually slightly soluble. So magnesium hydroxide is slightly soluble in water, and when it dissolves or ionizes in water, it's going to generate Mg2 plus and then 2 hydroxides. Those 2 hydroxides are what make the difference because they're going to increase the concentration of hydroxide, which is going to increase the pH of the solution. So by adding magnesium oxides or metal oxides to water, they hydrolyze the water to produce those hydroxides. And depending upon the solubility, they'll also increase the pH in the solution. Solid potassium oxide is dropped in water. So this is the same general idea. Maybe pause the video, see if you can do this one on your own. And if not, or once you do, go ahead and resume the video and take a look. Okay, so potassium oxide, K2O. And that's going to, when it's put into water, form that O2 minus plus 2K plus. And it's that O2 minus that's going to interact with water, H2O, and that's going to form 2 hydroxides. So those oxygens are just teaming up with the water to form 2 hydroxides, and really so that oxide isn't really going to be in there anymore, just an intermediate. So then K2O plus H2O is going to turn into K plus hydroxide, and there would be 2 and 2 right there. So as a result, the concentration of hydroxide goes up, and the pH also goes up. So, hey, if you caught this, you're noticing that I leave that K plus in there. But Mr. Jones, you said to always leave alkali metals out because they're always spectators. Notice how it's starting off not in a solution. So this is solid potassium oxide, which means it is not ionized on this side. So on this side, on the reactant side, we're not looking at ionic potassium. We're looking at potassium oxide solid, so it's bonded together. After you put it in water, then it causes it through this reaction, this little apparatus up here, to form K+. That's why we leave it in the reaction in this case. What's that you're saying? So what if the salt comes from both a weak acid and a weak base? That is a great question. If that happens, that means that we're going to have, so right here, we have ammonium acetate. So ammonium acetate produces ammonium and the acetate ion, both of which we looked at earlier. The ammonium ion is going to cause the pH to go up. The acetate is going to cause the pH to go down. This guy is going to generate hydrogens. This one's going to generate hydroxides. So what happens then is we have little or no overall effect on the pH, because both of them are going to be adjusting it. So one's going to increase the H pluses, one's going to increase the OH minuses. Those will combine to form water, and so they kind of neutralize each other. However, there will be slight variations to the pH if you add something like this to water. And in order to really figure out what the pH is going to do, you have to look at the Ka and Kb values. So if you look at the Ka and you look at the Kb, if the Ka is greater than the Kb, that means the solution will be slightly acidic. So we're going to say slightly acidic. But if, on the other hand, the Kb is larger than the Ka, that means the solution will not be slightly acidic, it'll be slightly basic. So to figure it out for this guy, you'd have to look at the Ka for ammonium and the Kb for acetate. And these values are given to us in our book. If you look on page 612 and 619, you'd see the Ka and the Kb for both of these. And in both cases, it actually turns out that the Ka and Kb are both 5.6 times 10 to the negative 10th. And since they have the same value, that means Ka is equal to Kb, which means that it ends up being neutral in the solution. with this particular salt. And one last example of this is just copper fluoride. So copper and fluoride, when they're in solution, the Cu2 plus and the F minus, copper can donate. It can donate H pluses, same way that iron did earlier when it surrounded itself with waters. Waters lost control of their hydrogens. And fluoride can accept H pluses. Okay, and it can do it by taking them off of water, thus generating hydroxides. So same thing in this one. We're going to generate H pluses, and we're going to generate hydroxides. Those two will cancel each other out. So this copper fluoride ends up being a neutral in solution as well.